Talking about the hydrodynamic analysis of floating wind turbines. I'm Muhammed. I'm doing PhD under supervision of Professor Elif Oğuz in the Civil Engineering Department. Okay, this is my outline. My presentation will be consisting in two parts. Firstly, I will give some theoretical basis. Then I will continue with the HAMS application. For the introductory remarks, I will have some one or two slides. Then I will continue with the floater design concerns. Then we will focus on the conceptual design approaches. I will give some details there. Then we'll be talking about the numerical methods of fluid flow. Then I will give more details about panel method outputs and the relevant codes we are using, and what we have compared so far. So at the left-hand side, you see the main foundation concepts in the offshore wind turbines. Beyond 60 meters, we are full of the floating turbines. So what's the main difference between the floating and fixed bottom turbines is the 6 degrees of freedom. Let me remind it again. In the translation, let me in translation, in the X direction is called surge, translation in Y is sway, Z is heave, and the rotations about X, Y, Z is the roll, pitch, and yaw respectively. We will come to that point later on again. Okay. So at the left-hand side, you see the harsh environment that the floating platform survives in it. And at the right-hand side, you see the counterparts of these dynamics. So from a design perspective, you need to start from scratch with the hydrodynamics, the platform dynamics, firstly, because of the stability issues. The other dynamics are the aerodynamics, mooring dynamics, structural dynamics, and control dynamics, but we need to start with the platform dynamics. So while doing the things from the scratch, you need to have some conceptual designs first. And by doing that design, we are at the lower fidelity region. To increase the computational efficiency, we are at the lower fidelity part. We are sacrificing the fidelity, the details, but this is for the sake of a higher number of geometry trials to obtain an optimization in this regard for the low fidelity part in this sense. So at the right-hand side, you see that the use of diffraction theory and Morrison equation is up to the dimension of the member. If the dimension of the member, the diameter of the member is less than the 20% of the wavelength, we are at the Morrison equation part. We omit the diffraction effects. The structure, the member is called hydraulically transparent structure. So the diffraction effects are omitted. On the other hand, if D over L is greater than 20%, then we are in the theory of diffraction region. For low fidelity, we sacrifice the viscous effects in this sense. So Morrison equation consists of two parts. One is the inertia part, and the other one is the drag part. If h by d, the wave height by the diameter of the structure, is larger, then we are in the drag-dominated part here. And if it's less, then we are in the inertia-dominated part. And especially these and the use of Morrison equation is generally for the jacket-like structures because of the smaller members we can use. But for the floating wind turbines, we generally use diffraction theory. For the diffraction theory, we're solving the Laplace equation. Let me remind you how we come to that point. For higher fidelity and details, we are using Navier-Stokes equations, but we come to the Laplace equation by assuming the fluid inviscid, thus irrotational and incompressible. So Laplace equation is satisfied in these conditions. So we gain an enormous computational costs in this sense. So for the numerical application, we are using the panel method codes. These panel method codes are the application of boundary element methods to the fluid dynamics. So we are only discretizing the boundary elements, while for the CFD, we are discretizing the whole domain surrounding our structure, a greater than the surrounding parts. So for a basic comparison, at the left-hand side, you see around 2.4 millions of meshes, and at the right-hand side, you see only around 1,000 meshes. And there's also more simplification. Let me show it in this table. And since our domain is only the boundaries, we are advantageous. For the numerically, we are full of stable in the panel method, while for the CFD conditions, we have some CFL conditions. And for the solution approach, we are not doing any iterative process. The solution is direct. But just the question is its applicability. And we show that by using these assumptions, we have already approved that we can use panel method for just the preliminary design phases of the structures, because it's valid to some extent, only some extent, but it's very useful for the conceptual design phases. Okay, let's talk about the motion dynamics here. At the left-hand side, you see a simple mass spring damper system, and at the right-hand side, you see the fluid forces are divided into hydrodynamic and hydrostatic forces. And for the hydrostatic forces, it's coming from the buoyancy. So F equals Kx, just the spring element, it's like considered like. So K is the stiffness matrix, hydrostatic stiffness matrix. So for the hydrodynamic forces, we have either in the wave forces or the radiation forces. Wave forces are consisting of the incident waves and diffraction effects. These two are accumulated together and called as excitation forces. And for the radiation forces, we have added mass, the mass surrounding the body of the structure that is needed to be accelerated while having a motion. And the out of phase, it's the damping, but that's not a viscous damping, that's the radiation damping. That's a potential damping. It's also called like that. That's not viscous, but it's because of the out of phase it damps. And so there we have the equation of motion. At the right hand side, we have some, and at the left hand side, we have something. And can we say that if we have the right hand side, we directly found the left hand side? No, for the regards of the floating bodies, there's a ratio between these parts, and it's called response amplitude operator. It's basically the response of the structure to the wave excitation. If let's consider that in a structure having so, some wave effects, if the waves are so small with small periods, then the structure will not be excited. And on the other hand, if the structure is facing with, let's say, tidal waves, then the structure will not fail. We will not feel it because the waterway will pass through under that. It can be thing like that. So we need to decrease this response amplitude operator. We can meet that's a um, that's a good point to start the optimization of this hydrodynamic analysis for a floating platform. So let's turn back to the general overview. At the left-hand side, you see the environmental conditions, and at the right-hand side, you see the modules of OpenFast. So what we have done is we are providing the hydrodynamic outputs to the hydrogen module. We have obtained these results with either panel method codes, one of any panel method codes, and we are providing it to hydrogen to make it generate some incident waves using inverse FFT, and it uses these hydrodynamic coefficients to emulate the platform in more higher fidelity of. So what we have done is providing these hydrodynamic coefficients to the hydrogen. Okay, what are these panel method codes? As Elif Hoca shows, there are many other codes, but I'm showing these four codes especially. Firstly, wave MIT, the wave analysis MIT code WAMIT is the first released codes and the most used one. That's the reason. And the other three codes are the open source alternatives to WAMIT. The first ever released open source alternative was NEMO from the Nantes laboratory, France. Then HAMS is released recently from a Japan scholar, Dr. Yingyi Liu. And most recently, the BAMUSE is also released, and we have included this also to our studies. And this belongs to Dr. Joseph Saverin. And so, how we compared these panel method codes? In four senses we have compared. And firstly, we have compared those regarding their responses to the mesh refinement. And then we have compared those with the direct results of these structures. They are giving the excitation forces, added mass radiation damping. So we have compared those results. And then we have questioned that if there is any difference between these hydrodynamic coefficients, does these effects reflected if we use past time domain simulation? Let's say if any divergence in the mass calculation, if it reflects to the resultant motion or not. We have questioned that, and after that, after obtaining the resultant motions from past, we have also questioned if any differences are there in the resultant motions, what can be the reason for that? So this is our conclusions. The results in the resultant motion data, the deviations are derived from the natural frequencies of the platforms. That's so much natural because during the resonance of any structure, it's hard to define its response. It's hard to define its the motion. So the panel method codes deviate around the natural frequencies. This is not an extraordinary case. So if we exclude these frequencies and look at the rest of the picture, we claim that we showed that in our studies, the result of motion differences are statistically insignificant. I mean, less than 5% deviation for using normalized mean absolute errors. And with that solution, thus we say that open source codes can be used in floating wind turbine platform dynamics. So instead of Vomit, we can use Nemo, HAMS, or BEMUSE. So these are our publications. If you're interested in, please look at it, check for those. And now we are at the application phase using the HAMS. Okay, these modeling phases are consisting of 3 steps: the pre-process, process, and post-process. Naturally, in the pre-process, we generate mesh and transfer it to the HAMS forms. We are transferring the mesh because it's originally Wamit's form, and we are providing the hydrostatic stiffness matrix. And then we are finding the environmental condition in the control file. Then we run the executive file, HAMS. The process is done by HAMS, and we are having the post processes. We have some files, and we are having, while having these files, we are comparing the results. We are doing the process on it. So regarding pre-process, let's dive into that. For the mesh generation and transfer, we are commonly using Rhino, and we are exporting the file in the Wamit's extension, .gdf file form. Then for the to use HAMS, we are using Wamit mesh transfer function of HAMS. It's called meshtra to obtain HAMS's mesh file form .pni. It's called, and then we are defining the hydrostatic restoring matrix, which is a product of Meshtra. It's already giving the results from it. We can cross-check with if it's available, or analytically, if it's simpler, you can cross-check. And then you need to define the environmental condition in the control file by following the instructions given in the manual file of HAMS in it. So after doing these works, we are running the executive file, and then we are obtaining some files. That one file contains added mass and radiation damping. That 3 file contains excitation forces, and that HST file is containing the hydrostatic stiffness matrix, which is actually the non-dimensional form of this K matrix, the hydrostatic stiffness matrix we are giving to the HAMS. It's turning back as in a non-dimensional form. It's just divided by rho times G. And we are using BAM Rosetta. We are recommending to use BAM Rosetta. It's beneficial tool. Okay. So for this added mass and radiation damping, you may handle it with Excel or any code, or you may use BAM Rosetta for quick checks, especially for the initial phases. You can use BAM Rosetta. You can compare your coarse meshes, fine meshes, finer meshes with that. It has a simple graphical user interface, useful, and you have options to quickly check the mesh and heal it, and you can handle the data easily with some statistics tools in it. So this is our structure for the application. We will use OC3 high-end Sparboy. This is from the top. This is from orientation view, and this is from the front and from the side. Obviously, the structure is symmetrical, so we will use 0-degree waves only. So while using hydrodynamic analysis, we are not at this platform-based cases while using PAMS, we are not defining the moorings. The moorings are defined in the OpenFast side. That's why we are using the 0-degree waves only for the spar buoy. We will be doing that. And regarding to drawing these structures, we will just draw the submerged part. Otherwise, Hans cut it out the unsubmerged parts with its own tools. But it's better to draw it in a certain way. So 10 meters of these 22 meters are unsubmerged parts. So we have a draft of total 120 meters. And the submerged part consists of 2 cylinders and 1 conical tapered body. At the upper cylinder, we have a diameter of 6.5 meters, and at the lower cylinder, we have a diameter of 9.4 meters. So that's all. We will be drawing the structure in a minute. Let me remind you the modes again. We will be using in the BAM Rosetta, so there will be no arrows there. For 0-degree waves, the translation in X direction is surge, and the translation in Z direction is heave, and rotation about Y direction is pitch. The rest of them are not used many, not used so much because of this symmetry of the structure. There is no significant sway, there is no significant yaw, and there is no significant roll. That's why we will be using the surge, heave, and the pitch motions. In the BAM Rosetta, we will be comparing those ones. Regarding mesh study, I will be showing just some mesh, some simple mesh, but you need to do some mesh independence analysis here also, like CFD. From a coarse mesh to the finest mesh, it increases the volumetric representation. While it doing that, the precision and the convergence increases also. The classification organization called DNVGL, one of the most important classification in this field, recommends a high volumetric representation and high hydrodynamic representation. It's recommended, but there's no strict rules, and so you need to use your engineering judgment. And I have used with these M4 meshes representing 99.4 of the volume is represented, and for the convergence, the difference between these M3 and M4 meshes up to less than a 0.5% is okay for me. We have accepted, and we have obviously stated. So we have used this M4 mesh, and these are my references. Thank you for listening, but we will come to that point, and I will recommend you to take a picture of that again. I will be drawing this structure, 6.5 meter diameter at the upper cylinder, 9.4 meter diameter for the lower cylinder, and there's a conical tapered zone with 8 meters of height. Well, the upper cylinder is 4 meters of depth. Okay, let's continue with the rhino part. So while it's opening, yeah, already opened. Well, so I will use the perspective view. It's simpler for me to represent the stuff. We will use these mesh tools at this upper tab, and we'll start from creating the mesh cylinder. And it asks us to base off the cylinder, and we have some options here. For the vertical faces, I will use 4, and for the around faces, I will use 24 here. And at the base of the cylinder, I'm using the free surface, and it asks me the radius. Radius will be 325 for the upper cylinder, and the end of the cylinder will be at the -4. Okay, this is the upper cylinder. Let's go with the truncated mesh cone. I will use 4 vertical faces and 12 around faces here. So I'm using the base of the truncated cone as from -4, and my radius will be the same with the upper cylinder, obviously. Then the top of the truncated cone, it asks like that. And the radius at the top is also 4.7. If it's already written there, you can just click enter and it creates the geometry. And beyond that, we need to create the lower mesh cylinder. And I will change these vertical faces to 40 and around faces to 12. While I'm selecting these numbers is to maintain a structure with more like equilateral form. In the CFD, we know that the side ratios are should be close to each other, should be close to 1. In this sense, it's also valid. So it's better to keep it as uniform as possible. So for the base of the cylinder, I'm using -12. I'm using a radius of 4.7, and my draft was minus 120 meters. So I have created 3 meshes, but that's not all. We have just 3 different meshes. We need to join them, but before that, we need to cut it if we want to gain more computational advantage. For coarse geometries, there's no need, but I will show you in case you will be using for the finer geometries. It gives, if you decrease to its half, then the mesh number, if the mesh number is decreased to the half, then the computational time requirement will be decreased to 1/4. That's why don't we use that option? Using mesh split by selecting the geometry I'm using, select the cutting object itself. Firstly, I need to create a cutting object. I'm writing a cut plane command. It asks me to objects for cut planing. Okay, I'm pressing enter. So at this point, for the start of cut plane, a unit vector is adequate, and Rhino is creating that cut plane, extending the structure. And okay, you need to click it enter again. Let me show it to the shaded form so that you can understand the geometry better. Now, okay, we'll cut the structure now. Okay, I'm selecting the structure and mesh split. It asks me to select the cutting objects. I have selected, and that's all. Okay, we need to check the details of the mesh here to see if there are some mistakes like this. There shouldn't be any bounding box with e to the minus some values. There are some problematic issues there. If you can uh, if you have better in the other side, you can use that. If you have both in a problematic way, then I recommend you to close Rhino and regenerate the geometry again, because fixing the panels takes more time than regenerating it. So I will close and redo it again if I have time. Okay. At the perspective, I'm using the mesh tools again. For the upper cylinder, I'm using 4 vertical faces and around faces of 24. My base of cylinder is here. My radius is 325. End of the cylinder is -4 meters. And for the truncated cone, I'm using it starts from -4 meters, and the radius at base, it's already saved, so we can use these numbers. And for the radius at top, we can use 470. Then I'm creating the base cylinder. I'm changing the vertical faces and the surrounding faces accordingly. Okay. I highly recommend to use the space coordinates rather than using the vertex directly. That's because Rhino have some issues with the panels, the mesh panels. So that's better. Let's say it. So the end of the cylinder is there. Okay, I'll be doing the same. I'm creating the cut plane. I have given it in a unit vector form. Okay, let me show it in the shaded form. Then I want to use the mesh split. It asks me to select the objects to split. I'm selecting the objects. Then it asks me to select the cutting object. I have cut it. And let me check if the problem persists or not. As you see, the problem is not persisting for the upper cylinder here. For the truncated cone, there's no problem. And for the base cylinder, there's nothing problematic. So I'm okay. I will delete this once. Now, from now on, we need to clear these interfaces. We all need the shell form in the hums and the other panel method codes. So I'm exploding these meshes and deleting these inner mesh faces. Do I have time to show something more deeply, or Nilay Hocam? How many minutes do I have?
Let me check. I think you have 10 minutes. So you
10
have
minutes.
Yeah, you have
Okay,
time.
well,
Yeah.
actually we need to do some treatment for the base and the top of these meshes. Since these meshes are not uniform, these meshes are not like quadrilateral, equilateral. The sides are not proportional. We need to change these meshes. We can delete and create some more meshes, but I'll need to proceed with these meshes, and let's see what's the form here. Firstly, we need to check if all the structures, all the meshes have outside arrows. So I'm writing dir command, the direction commands, and I'm selecting the meshes. If all the meshes pointing out, if the arrows are towards outside, then it's okay, there's no problem. So we can join the structures. If not, you should reverse the problematic meshes. Then you will need to continue. In this time, you can continue, but I highly recommend to use this quadrangulate mesh option. Sometimes vomit the rhino is not showing some triangular meshes. There are some triangular meshes there it creates while cutting the objects while it's slicing. But if you use this quadrangulate mesh option, then it makes all the thing in quadrilateral form. As you see here, there's something missing. We may directly fix this by deleting it and redoing and doing a page in here. Okay, I'm doing it again. And I'm deleting this page. Sometimes it does not work. Let me do it in another way. Okay, and let me delete this face. No, sometimes merging is not doing good. Sometimes this mesh patch is not doing good. Let's check the direction. It's pointing outwards, so there's no problem. You can use this mesh, but to listen the mesh numbers, if there are lots of triangular meshes for a fine mesh, you should carry out. You should think about that. It's better to form the geometry again, but for a coarse mesh, that's not a problem. So after creating the geometry, I need to export this mesh. I'm selecting the geometry. I'm going to File tab, then Export Selected, and I'm doing it into the mesh converter. I will use that in there. So for the vomit file form .gdf extension, I'm saving in this form, and I will use the name of OC3-coarse mesh to make it obvious to all. Okay, there's problem. So let's do it again. Let's say OC3 hyphen, just that, and save as type is vomit GDF. Okay, let's save it to in another position. Into downloads, let's say OC3 island, let's say. No, sometimes vomit getting trouble a little bit much. So if you have a valid mesh, then you can continue. I will show you the rest of the parts with my own meshes, and so actually this is okay. This mesh is okay. Okay, I'm closing it and I'm continuing with my own meshes, what I have created previously. Okay. In Helms Master, you need to download this Helms using Helms İngiliu. This is the link to download Helms. from GitHub. You just click on this code button, this green button, and download the zip. You can use from there. And I'm using the already done version. Okay, let's remind some what we said that we need to make a pre-process. We need to generate the mesh. We assume we have done it. In GDF extension, we assume we exported it. I have done it before. I will use those files. So I will use the mesh trans functions in HAMS. In this mesh converter folder, we are going inside. Then we need to copy this file to here, or otherwise you need to change the direction of the file from here. Okay, you need to change this name of the file. This shows that the file is in this folder. Okay, you need to change the file name. Accordingly, I'll use this file name, so I am keeping that. And you need to check if the center of gravity and center of rotation are in the global 0. If it's not, please take it to 0. Otherwise, OpenFast double counts it. If you are giving the center of gravity properly in here, then OpenFast counts it again, and this makes some missing some wrong calculations. That's the point to use mesh trans here. What do we need to do is just clicking the executive file. Okay, all is done. What do we have is the whole mesh, the water plane mesh here, and the hydrostatic input file. Before doing that, let me do another one. Okay, I'm going to the certification test folder. You need to create a certification test folder from copying any of the structure here. You have a folder now here, including some files. We will change those, but we need those files. Let's say OC3 fine mesh as a name. Then for the input files, we will go to there, and we need to copy this water plane mesh and whole mesh to drag and drop to here. We need to replace these files. Okay, and then we need to change the hydrostatic in here. The restoring there's a hydrostatic restoring matrix here. We need to change the information in this to obtain a proper HST file. In here, Muhammed Meshtran prepared a hydrostatic in file here. We are copying this matrix to the other one, to the selected one. Okay, let's do it in proper form. Okay. Actually, there you can input some external linear damping, quadratic damping, the restoring matrix. If you have knowledge, you can input those knowledge, and also the body mass matrix form. The hydrostatic in file actually contains the mass matrix. However, the results other than the mass is not proper because to obtain a proper inertia matrix, you need to have input the steel thickness, the ballast water, etc. So those are not true. But from the submerged volume, it calculates some mass matrix. It's excluded the mooring lines. You can use it's your option. Okay, just be sure that you are changing the hydrostatic restoring matrix and save it. Okay, after doing that, just the control file remained to be changed. Okay, let's do it. For water depth, for this OC3 high wind, we are using 320. If you input as negative, then it means infinite depth. Okay, for the infinite frequency limits, I recommend you to calculate, to make it calculate, so to include it. And for the input and output frequency types, we have options here. We can have the deep water wave number, finite depth wave number, wave frequency, wave period, and wavelength. Here I'm using now the wave frequency in radians. So I'm creating it from 0.25 to a greater point. So it's basically, okay, let me skip that file. Okay, my starting frequency is here and the frequency steps are there. If we use this minus sign, then the steps will be used. If you don't use this minus sign, you need to write all of the frequencies here. If you're interested in irregular frequencies without using any steps, you can use those. You can write it on your own. For the number of headings, as I said before, I will use just 0-degree waves, so there's no heading step I will use. And for the diffraction solution, let's take all of these as the same. Just for the number of threads, you need to check from task manager how many processors do you have. So from here, for the parallel processing, you have the logical processor knowledge from here. You need to check this number. If you want to use all of your cores, you can use this number. So that's all. I'm saving this. And what I do is just running the hums, the batch file. Okay, it works. If you see that sentence, that's okay. And you need to go to the output. And for the vomit format, we will go into that. And the results are named always as boy.1 and others. I highly recommend you to use BAM Rosetta. Just as similarly, you can use GitHub to download it. Some executive file is missing in that. You need to take it from this releases part, by the way. Let's turn back. By using this BAM Rosetta for these hydrodynamic coefficient tabs, if you drag and drop any of these files, then it takes all of the information from there to there. So I have created so I wanted to schedule, I wanted to take the axis from 4 seconds to 25 seconds. That's why I have arranged it has become begin with 0.25 radian per second to that much. So I'm showing you here is the added mass in dimensional form. You can use it in non-dimensional form. It divides for the appropriate numbers for that. And you can show it in the radian forms. You can show it for the radiation damping. This is the surge, this is heave, pitch, etc. So on its own, it seems nothing. Okay, what's that number? What's the use of that number? So we need to carry out some mesh refinement study. Before this presentation, I prepared one. So I will use these ones. to show you how it works. Okay, for a search added mass, it's not that simple to show. Maybe no. Okay. In this form, you see that this purple one is the coarsest mesh, the M1, and the difference between the M1 and M2 is great. Then it decreases, then it decreases. So obviously it won't be something visual, but for a quick check, it's beneficial to use BEMUs. And after that, you can use some data analysis. It includes there also. So you can select some of these and you can check the maximum, minimums, the averages, etc. You can use these other options to handle the data. It's beneficial to use that. So these are all I have to show. After implementing this mesh mesh refinement process, and obtaining an exact solution, there you see we are obtaining a resultant mesh. So as you see here, for the heave radiation damping, especially the M1 is the very distant from the others at the peak, but M3 and M4 are really, it seems for this scale, are really close to each other. As I said, as I showed you with this presentation, the precision and convergence increases. These numbers are the average of the average. The mode is averaged, and the excitation forces, added mass, all the stuff are averaged. That's not that much simple, but I made it simple for you to understand. And now my finest mesh will be used by Putra to show you how it works in OpenFast. That's all for me. If you have any questions, I may answer, or Putra can take all.
Okay. Thank you. Thank you, Muhammed. It was a really nice presentation. I don't know if there's questions. Maybe everyone is tired. They may feel tired now after very good presentations. Thanks for waiting until the end of the training. So we will continue with the Muhammed, but maybe I can repeat. If you have questions, you can write to us anytime you want to. So we can try to answer. Thank you again.
You're welcome, John.
Now we'll continue with Muhammed Putra.
Sure. Could you hear my voice?
Yes. Mm-hmm.
Okay, so I will share my screen first. Okay, hopefully you all can see my first screen.
Yes. Mm-hmm.
Okay. Let me swap it.
Okay.
Okay. Good afternoon, everyone. Thank you for staying up to now. Actually, I am the last presenter in here, so I will not try to explain too much here. But my name is Muhammad Juanda Putra. I am PhD student in Civil Engineering Metu, supervised by both Dr. Elif Ous and Dr. Nilai Cesar Uzal. And last year, I have already delivered presentations about OpenFast actually, and it is mainly done in Windows. And I have explained actually what's the input and output we can get there. So it's also recommended to check the OpenFast demo from last year from Tuba's YouTube channel. But today I will just briefly remind what is OpenFast and what can be done with that. And then I will directly jump to hands-on activities in Truba this time. Okay, so this picture has been portrayed many times. It's just a reminder that OpenFast is actually modeling tools we can use, and it contains of multi-physics calculations from aerodynamic, elastodynamic, which is structural, control, hydrodynamics, mooring lines, and etc. And OpenFast has also been validated against all kind of means, like with the real turbine, with the lab experiment, and with another code, as you can see here. And okay, so this is also important to understand. Yeah, this is degrees of freedom, which is exists in offshore wind turbine. This is actually omitted in offshore because the value is very small. So you can see the surge, sway, heave, roll, pitch, and yaw in animations here, so that it's clearly for you to actually visualize this. Okay. So once again, OpenFast is multi-physics simulations. We can do this kind of thing, combination of loads, wind, wave. As you can see here, I try to actually visualize NREL 5 megawatt atop of a semi-submersible. As you can see here, this is the generated power. And as the turbines moving backward, so surge positive, as you can see, the power is actually dropping because the relative velocity is actually less filled by the turbine. So this is actually important for us to understand that offshore load is actually hydrodynamic load is important in calculations of offshore wind turbines. We can also plot here the tensions in the fairing lead and anchor. Actually, so in the fairing lead, it has slightly higher tension due to it's also contribute. It's also actually calculating the weight of the mooring lines. Okay. We can also try multi scenarios here actually. So I try to simulate actually one emergency stop in windstorm cases. So let's wait until 40 seconds. So I introduce 42 meter per second wind speed here. And as you can see now, the turbine is under emergency stop. We can simulate this kind of things also in OpenFast. On the other hand side, I simulate turbine restart. So it's from actually resting position and I try to rotate the turbine. After 10 seconds, we can see the rotor has already been spinning, but still no positive power generated. After the turbine reach actually some optimum point, then it start to generate positive power. As you can see now, the power has climbing. Okay, so let's move on. OpenFast can also be done to simulate these failing cases. This one I simulate here is when we lose one of our mooring lines, as we can see how much our structure is actually being carried by the wave under 100 seconds. As you can see, it's already moving 100 meters behind. So this kind of things can be done with OpenFast. Nowadays, NREL also try to actually expand the capability of OpenFast so that we can also simulate a full wind farm with OpenFast. And this one I show here actually consists of 2 instances of OpenFast. So each of this turbine is one OpenFast. And now it's parallel with multi-threading, but keep in mind the one I'm showing here is velocity magnitude, so it's not actually flow profile. So we don't have the turbulence wake like the rotating shape and everything. The one I show here is actually the wake velocity. So it's relatively lower velocity compared to the surrounding. That's why it's emerging because I hide the other velocities. Okay, so several test cases actually already available inside OpenFast repository. This one is for fixed structure. We can see monopile, tripod, jacket, and for floating we have barge, spar, semi-submersible, and TLP. So all of these are available together with actually some other cases, even for this one, marine hydrokinetic. So they start to use OpenFast also for not only wind turbine, but also for another turbine. This one is actually floating marine hydrokinetic, and this one is fixed marine hydrokinetic. Okay, so actually that's all from the presentations. I will focus my effort on the Truba. Let's see. By the way, I have to mention first, this is a very important site. Just type OpenFast GitHub, and you can see this repository actually. So everything about OpenFast is in here. This is the OpenFast itself. This is the RTES, and this is the controller. So inside OpenFast, for example, you can see the manuals here, in which if you open, it contains all the theory behind OpenFast, and it also contains this thing that is very important, that is the out list parameter. So it is the output list of what we can produce from OpenFast, and it looks something like this. So for aerodynamic, we have a lot of outputs we can produce. We have for each of this module, beam dynamic, elastodyne, and everything. Even we have for the fast pump and so many other modules. So I recommend you to read the definitions of this output, but just output which is important for you, because otherwise the output files will be very heavy. Okay, so OpenFast is actually runnable in Truba, but it's not actually built in, and I actually build it my own. Wait, I have already prepared actually the installations document, but I will not do it again, and I will probably just attach it later so that you can build OpenFast on your own on Truba. So it's only 5 pages, not so long, but it takes actually almost 2 hours. So that's why I will not do it today. Okay, so this is my Truba account, and inside my Truba, actually I have OpenFast. So if I change directory to OpenFast, this is what you will have after you follow my installations. So we will have this kind of thing. Actually, I also make this cases folder so that I can simulate whatever I want, because actually after you follow my instructions from here also, you will also have this R test, and inside the R test, let me show you. So inside R test, inside glucose, and then fast pump or open fast, you will have these test cases actually: 5 megawatt land basis, monopile, spar, 3-pot jacket, and etc. So following the instructions I will share later, you will also have it actually inside the reg test and then R test, if I'm not mistaken, glucose. Okay, so inside here, if you move to open fast, okay, you can also have all of these cases ready. And the way I'm doing it, actually, I normally didn't work inside this repository. I like to work outside so that I have this case bank actually untouched. So normally I just, where am I now? Okay, so cases. Okay, saya for this simulations, I copy this OC4 SPAR so that we have a continuous, actually continuous tutorial based on what Muhammad had done before. So for that, I copy 5 megawatt OC3 SPAR and then 5 megawatt baseline here. So inside the baseline turbine, we will have actually several common things. Let's just see 5 megawatt baseline. And then so you have the servo data, the aero data. So this is common actually repository for NREL 5 turbine. So let's come back to our cases. Oh, sorry, from here. Okay, I also showed earlier that we need controller for OpenFast, and this controller actually has different dynamic link if depending on the how to say operating system. If you're using Mac, Windows, or Linux, for Truba, actually you can clone this repository and then build it. So let's just try that actually. So okay, actually let's just clone the repository. Wait. So it shouldn't be long actually. So I clone it and I go inside the repository. So from here, let's make a directory called build and then go inside the directory. We can see there is nothing now, and we just need to CMake it. So before you have to load CMake and actually GCC compiler. So if you make it, shouldn't take long also. Okay, and then make. Now you have all these .so files, and this .so files is the one we are going to use inside Truba. So if you just copy all these .so files inside the Servo data, so OpenFast case is Servo data. Now we can see in here, if we go to Servo data, okay, we should have this .so files, and it's important to have it if you want to run the 5 megawatt NREL 5. Okay, so I will run one simulation cases now, and then let's do that. We can go to home, and then OpenFast cases. Okay, so inside OpenFast, we have all of these things, including the bin. Actually, inside the bin, we have all the applications. Okay, so we have, after building it, this is all the applications you will have. FastFarm, OpenFast itself, and if we just try to run that, sorry, where is it? Okay, as you can see, it detects all of the thread we can use actually in Truba. So 32 threads for me, which is quite good actually. Okay, let's just focus on one. Okay, so come back. So let's see. And by the way, this is folder Muhammed sent me in HAMS. So it contains the hydrostatic actually coefficients like .1, .3, and .hst. And this one is the folder I will use later in my OpenFast folder, and it's actually in here. So if we go to 5 megawatt OC3 ls. Okay, where will we use the file that Muhammad created is actually inside this hydrodyne.dat. So let's try to see that. TI hydrodyne.dat. Sorry. Oh, sorry, I see my mistake. I should put star in here. Okay. So actually it's like this. Originally from the R test, they are giving us this, and this file is actually pre-generated with WAMIT, but we can also use what Muhammad has built earlier, and thanks to Muhammad for that. Oh, sorry. And just type insert and then change this. So it's should be here, one folder behind HAMS, and then this is the folder name. Okay, right and quit. Okay, let me clear this first. And then how to run OpenFast? Actually, we can submit a Slurm job, but since this one is actually quite short, so let's just try to run. So inside the binary, I have the applications OpenFast, and then in here, the folder name is with FST extensions. So if we run that, we should have something like this. I have to mention that OpenFast is actually not it's not parallel, it's serial, but we can run OpenFast in batch cases, which means that we can run multiple instances of OpenFast. So if we want to simulate wind farm from wind turbine from 3 meter per second to 25 meter per second, we can run directly all of it, like 3, 4, 5, like 23 cases all the same time, because in Truba I was given 32 cores, so it's actually one single run in Truba, and it's, as you can see here, open fast is very fast. It's really real time for 60 seconds. It's almost finished now. Just a little bit later. I just want to see the final result. So we want to simulate 60 seconds, and we need almost 40 seconds for that. So open fast is for these test cases is 1.5 times faster than real case. So this is why we need actually some this mid fidelity simulations, because if you are working with high fidelity simulations like LES or DNS, like all my colleagues has performed earlier, actually they use OpenFOAM and SU2. If you run the full wind turbine there, it takes actually I believe days to weeks, but in OpenFast is fast. So that's why we the intention to develop OpenFast is not to eliminate those results, because those are high fidelity with highest actually degrees of accuracy. OpenFast on the other hand has a little bit, not a little bit, it should be called mid fidelity or actually engineering fidelity. So we can run more cases in OpenFast and pick several actually critical cases and then bring that to high fidelity, so that we can actually use this thing to support the high fidelity simulators. Okay, so after we do that, we will have all of this summary output and everything, the things like I showed last year. And then I have actually twin of my HPC in my home computer, but I didn't know the mount options earlier. Thanks to Hussein, actually, I learned something very useful apart from the real material itself. So I will implement that later. So the same thing inside cases for me, and then in here, I also have the same things. The good thing is that, okay, let me show first what is this output file looks like. So, okay, it's actually text-based. Like this is the first column is the time and everything, and this is all the output we generated. Actually, the one from the Excel earlier I showed you. And this is the one we requested from the files. So we have wind velocity and blade pitch and everything, all the way up to the tensions in the anchor and etc. So the good thing is BEM Rosetta, the one that Muhammed explained earlier, also have the capability to read these output files, which should be good. Okay, if it's like that, it's because we have the last file of this with empty lines. Just erase that and save it. Should be good now. Okay, as you can see, we can plot directly open fast output here. Actually should be in real time if we run it together with open fast. So we can just click load in here, and then the plot will be generated in real time. So 60-second simulations, the blue line show the blue line show the power, and then the green line show the blade pitch actually. So this is one thing good that we can use OpenFast and BEM Rosetta together. And by the way, to produce this, how to say, the animations in the FST file here, we can go down and select in here. So this is visualization toolkit. 0 is for no visualization at all. This one is the fastest one, as I showed earlier, actually. So 60-second text took actually 40 seconds to complete. If we change this to 2, then we will generate animations. And then we can change this to 1 to change actually into surface representations. And if we run these things, then later we will produce VTK files. Let me not run it here because it takes also longer time, but I have the files actually ready. So let's see what's inside that. Okay, let me close this. Also, yeah. So from here, It's in my desktop, Truba, PTK Spark. So this kind of thing we will generate if we allow the visualization toolkits. Let's just plot these things and apply. So yeah, actually it shows the spar and the mooring lines and etc. And it's actually in time frame. So I tried only for 5 seconds and it produced 80 frames. So let's see the last frames. For example, it's like that, and it's you can produce animations, of course, from here, like the one I showed earlier in my presentations. Okay, so okay, since we have all of this ready, just move back, and then I actually have another things here to run. Let's see. This TS inflow is actually coming from the open FastPump actually test cases, which is retest, RTest, glucose, FastPump. Yeah, from these two test cases actually. So it should be the one I copied to test cases here. Let's run actually some of it. I don't know whether I should run it in here or let's just make slum job vi job dot script like this. Okay, so okay, where is the job script? So that we don't have to create everything from the beginning. I have okay. This is example of job script we can create. Let's just run some of it so that we are conserving times. Okay, so I will run two cases. One of them inside this TS flow curve. One of them is the one I just ran earlier. Okay, so escape, right and quit, and then S batch job that hopefully it's running. Okay. Okay, it's running now. Let's see inside my 5 megawatt baseline. Inside the servo. By the way, for one of these test cases, let's just show from here actually so that it's simpler. In Servodyne, for example, in here, there shouldn't be a problem. Okay. Let's just first copy discon. Copy discon dot show into discon dot discon2 dot show. Why am I doing this? Because most of the time, if you want to run two wind turbines in the same wind farm and it's exactly identical wind turbine, it is recommended to have also two controller and two elastodyne so that you can have different initial actually positions and then different controllers. Sometimes you want to yaw one turbine and then not yawing the other. We want to have this kind of configuration so that it's better if we have more also these controller things. So let's see. Okay, TS. Let's see whether I have successfully run this thing. Yeah, looks like I failed to run this one case because as you can see later here, SVD vt2.dat. Yeah, we need different controller here as you can see in Servodyne. it should be like with controller 2, but I haven't done that earlier. So that's why it's failed to run these cases for me. Okay. And by the way, let's see whether it's finished. Yeah, it's finished, but I didn't get the output here because yeah, I failed to run this code actually. Okay, so if we resubmit this job, SQ. Okay, it's running. Okay, change directory to TS. Oh, cool. Okay, as you can see now, I have the output here like fastfarm.output. Earlier, I don't have it in here because of the controller issues. Now I have it ready. So, SQ. Okay, actually all the jobs is finished. Let's see what I have. Yeah, as you can see, I have created 2 jobs running all together. One of them for one single OpenFast, and the other one is for OpenFast wind farm. So I have output from one turbine, actually 2 turbine, turbine 1 and turbine 2, and the output from the real farm itself. So fast farm output can also be shown in here. So let's just BEM reset again. I have completed the same simulations in my own computer. Cases here. Let's just show in here. So the binary in here actually is for the turbine. Is it okay? Okay, so we have, for example, cases. The things we don't have, why we don't have power, I think because in my original computer, I didn't enable this thing. It should be 5 in here. So when I run these simulations in my computer, I think I forget to change that to 5 because originally from NREL, it's like that. They don't actually employ any controller for this TS school. That's why we don't have power in there. So that's the actually reasons for that. If you run the simulations on your own later, don't forget to change that to 5. Let's see from the other whether we have, okay. See, for this thing, the one we have changed with 5 and then the correct controller, we have power actually output. So don't forget to change that because it's very important. Okay, this is from one of the turbine. We can change actually to model the other turbine. So as you can see, after some point, the wake hits and then the power drops. So it's actually better to simulate all of it together. We can also produce simulations of these turbines in here. For example, how do fast farm looks like actually? So this is actually combinations, compilations of multiple fast instance. For example, in here, so it's very important to see these files because this is locations of the first turbine at 0, 30 meter, and then 0 in Z. And then I call this one instance of OpenFast. And then the second OpenFast turbine will be in these coordinates. So in simulations, I think I have it. Sorry for rushing. Actually, I'm trying to fix the time. So I'm trying to catch 4 minutes. Let's see what I have it here. So for if you enable visualizations in fast farm, actually you will have 2 VTK. VTK FF is VTK for fast farm and VTK normal is for the turbine. Okay, so let's just try from here. We can bring all of this first. Okay, it takes sometimes for my computer because I'm opening another applications as well. Okay, so this is the visualizations of the two turbines. As you can see, it is not aligned in the X directions because from here they have actually 30-meter actually separations in the Y. That's why we see some shifting in here also in the Y. But you get the general idea. And then there is also one more visualizations we produce from FastPump. Let's also see in here so that it's clear. Visualizations. If we enable this, we have the low and high actually undisturbed data. So low and high resolutions undisturbed data. And we can actually take some slice cut of that from here. 0, 0 means there is no slice cut. So this 90 will not be executed. But if we enable 1, for example, it will take 1 in XY plane that is at 90 meters. And then this is for the YZ and XZ plane. So if I'm not mistaken, in my simulations here, I enable one of it actually in here. So it's at 90 meters here. So you can see at 0 time frame, there is nothing, but at 200, there should be something. Okay. Why you don't see it? Because the scale here is actually from 12 to 12. So let's try to plot something like from 6 to 12. So you can see this is coarse actually wake shape of one turbine hitting the other turbine. But I normally didn't really like to use this because producing this also takes some power of my computer, actually some memories. Let me show you how much is that. It's important to realize this thing. Okay, so for 100 seconds, I produce 60.7 gigabyte memory actually. So normally we didn't do simulations in Truba because it's also hectic to download it later. So if you want to run simulations, just use our own computer. And this is what I want to show. Again, like we also produce, if you also produce here with True, we'll also have this actually low and high resolutions. Let me show it in here. Okay, let's wait a little. Okay, so I will just spend actually just 1 minute maximum if my computer is working. Okay, so this is high resolutions for one turbine. As you can see, small boxes like this because it's the outline actually. And what I normally use is this. So let's just not showing this. So for the low resolutions, we can change this to velocity. We only have velocity because this is not actually high fidelity code. Velocity and magnitude, and then we can change that to column rendering. So this is actually all the velocity magnitude of the file inside this low velocity range. We can play actually with the transfer functions. This is what we call as transfer functions. So in here, if it's like this, so we put importance on the high velocity. But for seeing the wake, we actually more interested on seeing the low velocity region. So we can reverse it to something like this, for example, and then yeah, just play with this. So I think it's something we can do. And as long as you bear in mind, the one we are showing here is the velocity magnitude representation. So it's not the flow profile, but you can see the wake shape in here, how the wake hits your second turbine. So it's not fully hitting the second turbine, it's partially hitting because we have 30-meter actually separations in the y-axis. I think it's good representations because if you see from OpenFast repository, everyone is talking on what's the best representations for the wake. You can see people are doing this with many slice cuts like this. Yeah, it's also useful and it's also actually very good representations, but we want to see something like this. And still actually like people are showing like just take slice cut and it's, yeah, you can show something like that. But yeah, for me personally, I like to tweak it like this so that I can see more. Hopefully I didn't make it very rush. If you have further questions, actually, I'll be happy to answer. Thank you.
Putra, thank you very much. It was very good presentation and very nice animations and simulations that we have seen, and nice usage of OpenFast for many different kinds of simulations. So it will be very good for the new beginners as well.
Yes. Thank you.
Yeah. And this is nice view also that you showed. Thanks for that.
You're welcome, Hocam. Sorry for being rushed.
No, it's okay. It's okay. We are on time. We have still time actually. If you want to add more, if you have some things on your mind, you can tell them, because
Actually, I want to recommend.
Okay.
I want to recommend that if you want to produce your simulations, so in my, I will deliver actually how to build OpenFast on Truba. So it has options to enable both OpenMP and single. Actually, for the calculations, it's faster to use OpenMP because if we have 32 cores, which means that we can simulate in a wind farm 32 turbines. And for OpenFast itself, we can simulate directly 32 simulations altogether. But for visualizations, if you want to enable visualizations of the turbine as well, it's better to use single. I know it's taking long time, but due to actually message interfacing between these threads, sometimes it creates bug for the visualization. So to visualize, it's better to use single thread actually. Yes, that's the only thing I want to.
Okay. Usually for computations, we should use the parallel job scripts to submit our jobs and to do the parallel jobs. You can do, as you said, many cases of OpenFast to simulate a wind farm. So they are basically separate. I mean, they are different from each other, of course, different cases, just run at the same time. But
Yes.
You are saying as a wind farm, they are interacting, right? So they have some interactions between them. So they need to communicate.
Yes.
And we can run it in parallel for 32 wind turbines. So that's very good. Of course, in wind farms, there will be hundreds of turbines. So you should be able to get, you can get more cores, of course, for your simulations. So you can ask for that, of course. And also for visualization, of course, it is usually not recommended to use the servers. So you need to download huge amount of data to your computer to visualize or to prepare the animations, etc. But if you can prepare some ParaView scripts, like some macros, maybe you can automate for the visualization creation of the figures. I mean, if you know the layout, so but you create many figures, many plots for different cases. Then if you can automate that, you can also run ParaView in the batch mode or in like macro mode.
I will learn that from SG.
I think Ezgi was also thinking about that. Maybe you guys can try. I don't know if it is easy to install ParaView. We haven't tried that, but we can try that as well on Truba, and we can try to use macros. Okay, very good job. Thank you. So I guess attendees also learned a lot. So it was a long day, but very nice presentations, and all together they showed many different kinds of simulations, and you guys, while presenting, referred to each other. So it's nice that we have a nice group working on wind energy, and with different tools we are trying to simulate complex problems. I mean, complex wind turbine problems. So it was nice to listen, all of you. Hopefully, maybe we can do for next time, for the future, we may also try to do face-to-face, small online real sessions if possible. It's also possible we can do that. And I also recommend everyone, starting to these topics or already know what try to improve themselves. They can try these tools and prepare publications, and we can also share knowledge through the conferences. So it will be nice to meet at some time in the future. Okay, so I guess I don't know if any other questions or any other things do you want to share, anyone, before closing up?
For me, it's good.
Okay. Okay, thank you. So thanks for everyone. It was nice to listen to you, and have a good weekend, hopefully, and see you around.
Thank you, hocam.
Bye then. Okay, thank you.
Thank you, everyone.
Thank you. Bye.
Bye.
Thank you all.